Hello, welcome to this course on optimization. So, in this lecture, I plan to cover basics of convex sets and related topics. However, before going into that, we need to cover some basics from real analysis so that everyone is on the same page. Um, so, first of all, I would like to define a metric. A space, a metric space. So what is a metric space? So a set X is said to be along with a set X is said to be a metric space along with distance function d if for every x and y belonging to x there exists d x y which is a real number, and it satisfies three conditions. So first is that this dxy is greater than 0 if x is not equal to y, is equals to 0 otherwise. Second, this dxy is equals to dyx, and this third is dxy is less than equals to dxz plus dzy. This xd is called a metric space. So note that this d function d, this is called as a distance. This is called distance. So the first one is telling here that if the 2 points are different, then the distance between them should be always positive, and it should be 0 if they are same. And this second is saying that the distance between 2 points, I mean this is symmetric, so distance from x to y should be equals to distance from y to z. And the third one, this is basically triangles inequality. So this xyz, then distance between x and y, this is less than equals to this the distance between x and z and y. So this is a metric space. For a metric space, note that if x and d is x comma d is a metric space, then y comma d will also be metric space where y is subset of x. So y comma d will also be a metric space because this distance function d will be defined over y also, because y is contained in x and d is defined over entire x. So one example of a metric space is like Rn and n in L norm. So this is a metric space. So a distance function is given by Lth norm over this real space. So d between x comma y is equals to norm of x minus y, right? So there are several examples of such metric spaces, and this distance function d, just to make this clear. So lth norm of say some z. This is equals to sigma like zi to the power l to the power 1 by l, right? So this is lth norm. So z is a vector and zi is the ith component of this z vector z. So this is metric space. Then next we will discuss open ball. So what is open ball? Let this point x belongs to so throughout we will maintain this notation x and d for metric space. So x is the set and d is the distance function defined over that set. So x belongs to this small x belongs to x. Then open ball, this is x, then open ball around x is defined as the set b. Okay, let's call this as small. So this x naught belongs to x. So this small ball around x naught with this open ball around x naught with radius r is the set of all points, all point x, such that distance between x and x naught is less than r. So this is open ball. So here this is strict inequality, and in closed ball, so I will just note the notation. So in open ball I denote it by b, and small ball and closed ball with b bar. So here we have the set of, this is the set of all x, is that distance between x and x naught is less than equals to r. So here we have this like this is not strict inequality. Next let's define interior point of a set. Interior point of a set for any set say E is a subset of x. So what are the interior points of x? So this is a set E. Any point x naught is called said to be an interior point if there exists some ball, some open ball around P. There exists some open ball, at least, because at least some for some r. I mean there should exist some open ball which is entirely inside the set E. So so x naught is this point x naught is an interior point of E if there exists some r such that b x naught comma r, this r must be greater than 0. This is this is completely inside E, then this is interior point. Next we look at limit point. So what is a limit point? Limit point of E. So note here, so x naught, a point x naught is an interior point of E if there exists some ball. So there exists some ball that or some open ball around x naught that lies completely inside E. While limit point of E, so x naught is said to be let's denote it as x1. So x1 is a limit point of E if for all open ball, x1 comma r, if for all open ball for r greater than 0, the intersection of this ball with E, I mean this open ball, every open ball around x1 intersects E at some point other than x1. So this is open ball around x1 and it intersects E at some point other than x1. So for all r greater than 0, fine. Then this is called a limit point. So we will take an example. So let's say our metric space is R and absolute value, so set of real numbers. So this is our metric space, and here this real line. So let's say this real line is so our E is X, E is also R. Then oh sorry, no, not E is not R. So let's say E is open 0 to closed 1 union 2, right? So this is 0, this is open, this is 1, and this is 2. So is 2 an open point for set, a limit point for set E? No, because we can take a ball around it and it doesn't intersect with E at any point other than point 2 itself. So point 2 is not a limit point. 2 is not limit point. 2 is not a limit point. So is point 1 a limit point? Yeah, I mean we take any small ball. So any small ball, so 1 minus epsilon. So for we take any ball 1 comma epsilon. So this point 1 minus epsilon, or say this point 1 minus epsilon by 2. So because this is open ball, so 1 minus epsilon by 2, this belongs to E, this belongs to this set for every epsilon. So for every such ball, this point always belongs to this set E. So E is so 1 is a limit point. Note that this limit point belongs to E as well. So 1 is a limit point and it belongs to E. Now is 0 a limit point? 0 is a limit point. Yes, of course, because again if we take any point ball around it, so note here, so epsilon greater than 0, so epsilon should only be should be always positives. So any ball with 0 center 0 and radius epsilon, and this contains point 0 plus epsilon by 2, and this is always belongs to set E. So 0 is a limit point because this point always for any ball, this point always belongs to set E. So and this point is this point is other than this 0 itself. So 0 is a limit point. 0 is limit point, and this 0, note that this 0 does not belongs to E. So we saw 3 examples here. So there are 3 points we took. So 2 is not a limit point, this 0 and 1 are limit points. What about these points in between, say 0.5? Clearly one can see that 0.5 is also a limit point. So note that every interior point must be a limit point. But inverse is not true. A limit point need not be an interior point. For example, 0 or 1, both these are not interior points, because the ball that we take here, so here we saw that for 0, 0 plus epsilon by 2 lies inside the ball, but 0 minus epsilon by 2 doesn't lie inside the E, but it lies inside this ball. So these are not interior points. Next, so here I just like to point out, see this 2. So here any open ball around 2 intersects E only at 2. So such a point is called isolated point. So interior point, there exists some ball that lies completely inside uh, the set E. There is limit point for which every open ball around it intersects the set E at some point other than at least at some point other than the point itself, and there is isolated point. So every open ball around that point intersects E only at the point itself, only at the point around which the ball is taken itself. So that point is called a limit point. So here 2 is a limit point. 1 and 0 are limit points. This 0 and 1 are limit points, and this open 0 to open, so this interval open 0 1, this interval open 0 1 is like set of interior points. Next, what is a bounded set? So what so just to recap, so what we have studied so far, so we saw the definition of a metric space. So metric space is a set of elements with some distance function defined over them, which satisfies these three properties. That firstly, it should be 0 only if 2 points are a distance between 2 points can be 0 only if they are same, and otherwise it should always be positive, so it can't be negative. And secondly, it's symmetric. So dxy is equals to dyx, and finally it satisfies triangles inequality. Then we saw the definition of an open ball, that set of all points around a given a point x naught, like the set of points around a point x naught at a distance less than r is called an open ball with center x naught and radius r. And the closed ball, if we have the inequality is not strict here, then we saw an interior point. So interior point is point around which, if you take there exists some open ball which lies completely inside the set. There is limit point, which we just saw, that for every open ball around the point, it intersects the set E with some at some point other than the point x1 itself. And finally, isolated points, that every open ball around the point intersects at that point only. Finally, this bounded set. Bounded set. So any set is said to be bounded. Set E is said to be bounded if there exists some x naught, or let's say x2 here. So if there exists some x2, so x naught we denoted interior points, so x2 we denoted x1 we denoted limit points, so x2, so that is just call this x2. So there exists some x2 and r such that there exists some r greater than 0 um, and some x0 some x2 belonging to the set E, such that open ball, I mean this E is contained inside the open ball B x2 R. Then this then E is called said to be bounded. So having discussed the definitions of interior point, limit points, isolated points, etc. So let's take one example. So let's say this x, the set x is the set of real numbers. Let's say this x is real plane R2, and E is a set of real numbers. So this is x, this is y, and this this is y and this is x, and here this real line is our set E, right? So what is the interior of this set E? We take interior of set must lie inside the set, so the point must lie on this x-axis. Then if we take a small like any ball of any size, so B, so let's say this point is x0, then any open ball B x0 comma R for any R greater than 0. So there a point x0 comma R by 2, say this point lies inside this ball, right? So if you just zoom here, so a point, so this is point, this is point x0, and a point this point lies here, this lies inside this ball, but this does not lie on lie inside E. So this ball is not, so there doesn't exist any ball that lies completely inside the set E around x0. So x0 does not belong to so x0 is not an interior point, not interior of E. So similarly, you see no point on this x-axis, or to be more precise, in this set E is an interior point of set E. So interior of E is empty, is an empty set. So whenever so we see that when this dimension so when the dimension of set E is less than dimension of x, then interior of E, I mean it does not exist. So for such cases we define relative interior. So what is relative interior? So it is denoted as relative interior of E. So this is the set of points, this is the set of points x such that there exists an open ball B x such that there exists let's say there exists R greater than 0 such that the open ball B x R intersection the set. So we will define what is this set. Affine E is a subset of E. So this is called relative interior of E. um, so a relative interior of E is a set of so what was interior of E? Interior was of E was a set of all points such that the open ball around it lies inside E, while relative interior is a set of all point X such that open ball around X intersection with E a set affine E. This lies completely inside. So to better understand this, so I will discuss what is this set affine of E. Basically, this set affine of E is the affine hull of set E. So for this, I will discuss what is affine set, of a affine combination of points, and a affine hull of a set. So a set A is said to be an affine set if for all points x and y, a pair of points x and y belonging to set A, comma the line passing through x and y also belongs to A. So you have to see this. So let's say this is x, this is y, and then this line is x comma y. So this line passing through x and y can be written as x plus theta times x minus y, where theta belongs to set of real numbers, and this can be written as okay, so write it like write it as x plus theta times y minus x. Then this can be written as x into 1 minus theta plus theta y. So this is the equation of this line. So for every x and y, this combination x times 1 minus theta plus theta y should also belong to A for all theta belonging to the set of real numbers. So such if set satisfies this property, then it is said to be a affine set. So now coming to what is a affine combination. So basically this combination of these 2 points x and y, this is called an affine combination of points x and y. So in more general terms, affine combination of a set of points x1 x2 to xn, its affine combination of these set of points is given as sigma theta I x I from 1 to n, such that sigma theta I is equals to 1. So for any set of points x1 x2 to xn, the affine combination of points is given as so this is said to be the affine combination of these points. And in a affine set, all affine combination of points are also present. And what is affine hull? So affine hull is the smallest affine set, affine hull of set E is the smallest affine set that contains all the points of set E. Smallest affine set that contains E. So how we get this? So we take every pair of points and keep adding all the points that lie on the line passing through those points, and we keep repeating it until finally the set becomes affine. So coming back to this relative interior thing, so relative interior is the set of all x such that there exists some ball around it, um, with radius r greater than 0, such that the intersection of this ball with affine set E is completely inside E. So we can look at it with a different example. So uh, so consider this example. Okay, so consider this example. So we have r2, so x is equals to r2. Inside x, this is this is the line E. So what is the affine hull of this point E? So this is the same as this. I mean, this set E is already affine. So we take any ball around this point. So this ball does not lie in E. No open ball about any point on this line lies in E. However, this open ball intersection of this with affine of E, which in this case is E itself. This, what is this? So if we zoom into this, so if we zoom into this, so this is the point, this is open ball around it, and this is the line basically. So this open ball intersection, this affine of E, this is this part of the line, this is this part of the line, and this is actually contained in E. So here we see that interior is empty for this set E. Interior is empty because about any point in this set E, if you take an open ball, it is not completely inside E. However, the relative interior is non-empty, because the relative interior so this is basically this set of these points, the intersection of open ball about any point in this set, if we take its intersection with the affine hull of this set, then it completely lies inside the set E. So having discussed this affine set, having discussed the affine set, we will next look at what are convex sets. But just to recap, so a affine set is a set in which for every pair of points, the line passing through that those points also lie in the set. So next we discuss what is a convex set. So in affine hull, in affine set, so for every 2 points, the entire line passing through those points should lie. However, in convex set, only the line segment joining these 2 points need to lie. So if we have these 2 points, only this, I mean, we only need to have so if there is any set C that contains x and y, so let's say there are only 2 points in this set, x and y, so it is not convex. But if this set contains x and y union the line segment, all points lying on this line segment x and y, this line segment x and y, then this is a convex set, because we take any 2 point on this line, the line segment joining these 2 points will also lie in so we take any 2 points, the line segment joining these 2 points will lie on the set. So we have, if we have point x and y belonging to C, then theta x plus 1 minus theta y should also lie in the set, but here the theta only belongs to 0 and 1. So if we only so to denote the points between x and y, the theta needs to be restricted to 0 and 1. This is a convex set, and this combination, so for any set of points x1, x2 to xn, the convex combination of these points is given by sigma theta I xi, such that sigma theta I is equals to 1 and theta I is greater than equals to 0 for all I, right? So earlier we had that the affine combination we had, that is sigma theta xi, such that the sum of theta is 1. Here we have an additional condition that each theta I must be greater than equals to 0. So we will come to more examples of this, because this is the focus of this lecture. But before that, I would also like to discuss what is a cone. So basically a cone is a set D or say a set C is said to be a cone if for all point x belonging to C, alpha x also belongs to C for all alpha greater than equals to 0. So what is the simple example of so note that if x belongs to C, then 0 times x also should also belong to C for the set for C to be a cone. So 0 should belong to C. So a cone must always consist of origin. So now, so we have a ray. This is a ray. Is this a cone? For any point here, let's say x. So does alpha x belongs to this this line, this ray, if and only if the tail of this ray lies on the origin. So if the tail lies on this origin, then alpha x will also lie on this ray, given that alpha is greater than or equals to 0. So this is a simple example of a cone. So is this the smallest cone? No. So take this point, the set of point origin, origin. So is this a cone? Of course. I mean, if 0 lies in the set, and every other point alpha into 0 is basically 0, that also lies in this set. So this is also a cone. So is this the smallest cone? No. Consider this empty set. So because no point lies in this set, I mean, so it satisfies. So what is a cone? So if any x exists in the set, then alpha x should also lie in the set. However, there is no point, so since there is no x, then alpha x need not lie, and this is also example of a cone. and this condition holds this holds for all these points here, um, all these points, all these sets, convex sets also. So in a convex set, if there is no so smallest convex set is an empty set. So if there is no point, then uh, then there is like there is no point to take convex combination, etc. And so the empty set is also convex, it is also affine, and it is cone as well. So uh, interestingly, this affine set, a set is the other than empty set, any single point, any singleton set is affine, because uh, there is no second point to take the affine combination. So every singleton set, so empty set is affine, convex and cone, and a singleton set is always affine and convex. But a singleton set, to be a cone, it should be the element of it, the only element of a singleton set, that should be origin. For a set, we saw what is its affine hull by taking convex, so by taking affine combination of points. Similarly, we have convex hull of set and conic hull of a set. So like affine hull, so the convex hull is the set of all points that can be obtained by convex combination of points in set C. So what is the convex hull of C? Convex hull of C, convex hull of C is the set of all points, is a set of all points y, such that y can be written as sigma theta I xi, comma, for all x, where xi's are the point, sigma theta I is equals to 1, where y convex hull of set C is the set of all points y that can be represented as a linear combination of xi, such that where xi's are the points in C, xi belongs to C, and sum of theta I is 1. Similarly, conic C is so conic hull of set C is, conic hull of set C is the set of, let's say, z, such that z is equals to sigma theta I xi and theta I greater than equals to 0 for all I. Okay, so now we will look at examples for these sets. So we have actually focused on affine sets. We have focused sufficiently on affine sets and conic sets. We will look at convex sets again. I mean examples. So convex sets. So let's see a figure for this. So conic set, so let's say we have the set. Of course this set is not a cone, because origin doesn't lie in this. If we join this line, so now this is a now this region is a cone, and this is the smallest cone that consists of set C. So this is the conic hull of this set that we originally had. Similarly, let's say this is set C. So this is certainly not convex, because this line does not lie in this set. However, if we add this, so make it more clear. So for example, if we have this set, so this is not convex, but if we add these points to this set, Now this became convex, and this is the smallest convex set that contains C. So this is called the convex hull of set C, right? No, convex set. So convex set. So this is a convex set because line segment joining any 2 point in this set also lies inside this set. Let's look at some example. So this is convex set, and this is not non-convex because this line does not lie inside the set. So some examples. So hyperplane. So what? So hyperplane is a convex set. So in any dimension Rn, hyperplane. So is this affine? So hyperplane. So if we take any point on this plane, hyperplane, the line segment joining these points also lie on the hyperplane. So this is certainly affine. And is this convex? Yeah, I mean, if this is affine, then this will also be. So if entire line lies inside the set, line joining the 2 points lie inside the set, then the line segment joining these 2 points will also lie inside the set. So this is so this is also convex. So any affine set is also convex. Is this cone? Origin doesn't like this. Is a easy check. So origin, if origin doesn't lie in this set, lie on the hyperplane, then this is not cone. But if origin lies on the cone, if origin lies on the cone, lies on the hyperplane, if origin lies on the hyperplane, then this is a cone. Then we have a hyperplane. So we had a hyperplane, then we have half spaces. So let's say let's look in R2 only for ease of like visualization. So we have some hyperplane, let's say H, then it divides the entire space in 2 parts, right? So each of these parts are called hyperplane, are called half spaces. So are half spaces convex? Of course, yeah, I mean, of course it can be easily verified. Are they affine? Are they affine? No, because we take any point on the hyperplane and a point on the and any point that does not lie on a hyperplane plane, any 2 points, like one point on the hyperplane and another second point in the half space not lying on the hyperplane, and then these 2 points do lie in the set half space, but the line joining these 2 points does not lie on the lie in the half space. So this is not a so half space affine, no. Convex, yes. Is this is a cone? If if this hyperplane passes through, if the hyperplane passes through origin, then the half space will also be a cone. However, I mean, as you can see, so we had this cone, so we just increase this angle, and we finally when we get this straight line, so this will be a cone. So half space is convex and is convex and cone, but not so if origin belongs to the half space, so this is conditional. Then we have then we have a ball, let's say a ball, solid ball, and say in R3 or R5. So let's say solid ball that consists of all the points inside the ball. So is this affine? No, because line joining any 2 points will not lie in the, I mean, because so affine space can't be bounded by a ball of finite radius, but I mean affine affine is not bounded by inside any. So we saw the definition of a bounded set. So note that a affine set cannot be bounded by any ball of finite radius. So but this ball is bounded and a line is not bounded. So no line actually lies in completely inside a unit ball. So unit ball can't be affine. So this is not affine. Is this convex? Yeah, this can be verified. So this is convex. Is this cone? No, again, because so affine, so it can be affine. So I am talking about unit ball of radius 1. So a ball can be affine only if it is singleton. So if only origin is there, or if there is only if there is only a single point. So let me correct myself. So a bounded set can be affine only if it is singleton. So a bounded set can be affine only if it is singleton. So is this is a cone? Again, so this is not so if this is a singleton and in fact this is origin, if the only element in the set is origin, then this can be a cone. Otherwise but unit ball is not a singleton, so this can't be cone, because again cone is also not bounded. So we saw here, right? So cone is not bounded, so it lies like infinite ray. I mean it consists of a ray. Ray is basically again of infinite length, I mean not bounded. What next? So similarly there are polyhedrons and polytopes. So we have like half spaces, they intersect and they give us polytope. Or so if there are a finite number of half spaces, like if this region obtained is bounded, then this is polytope, otherwise it is polyhedron. So this is this affine? So let's consider this bounded set here. So this bounded set, this bound so let's just polytope. So polytope is convex. Polytope is convex. Polytope is convex. Is this affine? Again, if this is not singleton, this is not affine. This is not singleton, so in this example this is not singleton, so this is not affine. This is not affine, this is convex. And if this is this cone, again, so this is bounded, so this is not a cone. This is neither singleton nor bounded, so this is not cone. So there are many such examples. So we looked at some. One can look for like more details in book Convex Optimization by Stephen Boyd. I think this is enough for an introductory lecture. So in next lecture we will look at convex functions and their properties. Thank you.